Okay. Wireline is a slick line in a way, is a single strand of wire. It is made with a high tensile steel. The reason we want high tensile steel because to minimize the diameter of the wire. Minimizing the diameter has several advantages. Because the diameter is reduced, the weight of the wire is reduced. Because when we go inside the well, the weight of wire will be added as you are hanging inside the well. So if you have more metal, then the weight is more. That's why we need high tensile steel. The other problem the other requirement to be supple enough to bend freely. Do you remember we have two pulleys? One is 180 degrees. Change in direction. Yeah. This is 90 degrees. So reducing the diameter will make it more supple. Minimizes upward force. So the wire on the surface the pressure is 0. Pressure here is 3000 psi. Multiplied by surface area, pressure multiplied by area become force. This is upward force. The higher the area, the higher the upward force. Okay? Is that clear? The friction in the stuffing box. Do you remember that a stuffing box at the very top here a stuffing box that has the duty of preventing leakage. So there are sort of glands that can prevent leakage. And if there's a leakage happening, we need to put hydraulic fluid behind this stuffing box. Now, if you have a large diameter wire, friction is applied to this area as it's moving up and down. if you have a small diameter, friction applied here. So which one has more surface area? This one. So more friction. Okay? And finally, another important point is that here we have this pulley, and on top of this pulley we have the wire. We have this wire on top of the pulleys, yeah. And it has a thickness. Now, this is the midpoint of the wire. The upper part is under tension. The lower part is under compression. Okay? As it is moving on the pulley and coming to this pulley, it is experiencing tension and compression. That will cause a corrosion that we call it fatigue. Okay? And that will cause the fatigue. It's like, you know, you have seen that if you have a spoon and you bend it repeatedly, it will break up. So something like this can happen and the wire may break up. So the best option to minimize the diameter. That's why we need high tensile steel. Normally we use 50% of the breaking strength. And if you have a stress, you need to take that into account. The length is 10,000 to 25,000 legs, and braided cable are used when higher breaking strength is required. But it is more difficult to seal around it. Any question? So this is some information for different type of cable. And we discussed length and tension. Is a popular exam question. Here you can see rope tension meter. That's the rope is going through the pulleys, as I mentioned. So you see that this is one pulley here. It goes through here and goes up. Another pulley down there, and another pulley, you know, here at the top here, and then go through here, and another one here. So that three pulleys are working together. This is what you see from control room, in a way. The operator, you see this. You see one pulley here, going over another pulley and going another pulley here. So this device is good for simultaneously measuring the length and the tension. So why pulley is required? I mentioned that before. And now, ability to work with a live well. How can the few meters of tools be run in the live well? The element you have salt valve here, lubricator, a stuffing box. This is a stuffing box. And then BOP. And we basically, what we need to do when we are running the equipment, we normally to have two safety barrier. So we close the top master valve, close the stop valve. That's two safety barrier. And then open here. Open this connection here. First, we need to bleed off any gas here. So we open the bleed off gas until the pressure stops. And then we have closed this one, close top master one, open this section, and connect the tools that we want to use on the wire, pull them up, and then put it here. Obviously, the length of lubricator should be more than length of the tools. Okay? And then close the bleed valve, open the stop valve, look for leakage. If there is no leakage, is open the master valve, top master valve. Then again, look at leakage. If there is, normally you have some leakage from here at the top, the stuffing box. So you need to inject the oil to push the sealing element to grab the wire more strongly. Obviously, there is a balance, because if you grab it very strong, then it's difficult to move it downwards. So there is a balance there. And then gradually let this tools goes down, initially very slowly, and then when you reach near subsurface safety valve, you can do depth coloration. Near the no-go, again do depth coloration. Below the tubing, again you can control because we came to casing. And then we, after finishing our job, we come up. And the section that we are coming up near the surface, we do it by hand. We pull this spring because machine may not sense it, and you end up cutting the wire. So gradually move up. Once we make sure that it is at the very top here, we close the bottom master valve, then swap valve, open the bleeding valve, this one, to let the gas to go out. This is the pulley and the bending moment that I mentioned to you. And this is the internal BOP, and this is bottom gland. This is top gland, and this is the packing. We put pressure in the gland to the packing to go prevent any leakage. This is BOP, blowout preventer. It can be single or can be double. This connection, there are pink end O-rings. So pink end O-rings, it will allow us to make connection and disconnect very quickly. So now, so far, we have the equipment for wireline. Now you need to connect the wire to the tools. So this is a wire, this is a rope, and you put in what is called rope socket. The wire comes through here and go over the device. So the wire coming down here, go over the device, and we pull it. And normally we make this point slightly weaker. You might say, why? Why weaker? We want everything to be strong. Why we do it weaker? The reason is that if tension is too much, we want it to cut from here, not from here, not higher. Because here you see that rope socket has a fishing neck, fishing neck. Yeah. And if there is a wire above the rope socket, you need to remove that wire first. So your overshot or devices that you have for recovery will not lock to the fishing net. Okay? Now, equipment, this is rope socket, and below that, you have the equipment. To the string. There is a stem. A stem is heavy cylindrical section that you add them together to overcome the friction, the buoyancy. So this is for downward movement. Yeah. Then we have jars. We have two types of jars: hydraulic jars and mechanical jars. Hydraulic is they use the fact that the friction in the fluid depend on the distance. The lower the distance between the jar element and the wall, more force need to be exerted. And that will create a hammer type behavior. And hydraulic jar is like, I think I have some picture there. Again, like a jar, but you can do like a hammer, but you can do hammer down or hammer up. So hammer down, when you touch the obstacle and then suddenly release the tension, and then it will hit the top of this lower section. Hammer up, you slowly come down and then pull very sharply. I think I have some video I will show it to you. Then you have ability to connect other section. This is what is called knuckle joint, because the distance between inside tubing and the tool string can be very little, and you are going to add more tubes at the bottom here, so you want to have some flexibility here. So a stem to overcome frictional and differential force, force equal pressure multiplied by area, and that, the rope, we explained that the pressure depends on the diameter. So that will be upward, because as we go deeper, now this stem will overcome that upward pressure, upward force. And a stem is available in different sizes. You see that this stem is slightly different. This is for inclined wells. If the well is not vertical, you want to minimize the friction between a stem and the wall of the tubing or casing. You put these rollers on this stem. This is the jar I mentioned to you. Jarring action, you see that it is now closed, it is now open. Let's see if I can show this video.
Sir, can I ask you something?
Please.
what kind of, at what dimensions are the jars about?
Say again?
Dimensions of the jars, more or less.
Oh, the diameter depend on the tools, you know, because you have these devices at different diameter. Yeah, because obviously it depends on the no-go diameter of the tubing. So tubing, we can have 4.5 inch tubing. You can have 7-inch tubing, and obviously, what will happen? It should match the. It should be smaller than the internal diameter. Okay. So is it different sizes? Depend. You can have a 7-inch tubing. Therefore, you can have larger diameter. Let's see if I can show this video. Okay, stop. Can you see the video?
Yes.
This is an obstacle. You want to pull it out. Pressure is building up. See that? Hydraulic jaw. Suddenly, jaw. See that? But not able to release, coming back again. Pressure build. See that? Now manage to pull it out.
Screwed into the bottom of the mandrel. Normally the mandrel doesn't have this part on it, right? Okay, this is just my means to push and pull. I don't have draw work, so
does keep the tension all the time. Normally you have to do several times to repeat. Here I can find anything on the mechanical job.
As the #1 provider of drilling tools, Weatherford offers one of the largest, broadest selections of oil-filled tools in the industry today. From conventional to groundbreaking, our technologies help you take on the most extreme environments, anywhere in the world. Weatherford's jars are recognized as the industry standard, and our offering includes an array of types and sizes of jars, as well as other performance drilling tools, such as slingers, shock absorbers, thrusters, and lubricated bumper subs. Let's take a look at some key features of a Weatherford drilling jar. One-piece involute splines provide maximum torque with minimal backlash while drilling. Fluid-isolated pressure chamber lubricates and isolates moving seals, impact shoulders, and mandrel from downhole debris to ensure operational integrity. The pressure chamber is unaffected by downhole temperatures and generates little heat when in use, resulting in consistent time delay, even in deep, high-temperature wells. Zero bleed-off.
This is a jar up action. Going back to our presentation, any questions so far? So mechanical jar, when you release the wire, it moves fast downward and hit this. This is called jar down. The other way, if you want to pull something, then you start from here and fast pull it up, pull the wire up. When you put the wire, normally we do it by hand. And then it will hit the top here and jolt the equipment for coming out. So we have two types of jar, hydraulic jar and mechanical jar. And then this is called accelerator, because when the hydraulic jar activate, then the tension is gone. But if you have an accelerator, then the tension will remain, and therefore it's more effective jarring. Knuckle joint is that provide, because this a ball and socket joint here help alignment of the tools inside the tubing and normally above operating tools. Yeah, at the bottom of the wireline equipment. Here, this knuckle joint. And then operating tools depend what type of problem we have. We have gauge cutter, impression tool, blind box, perforator, running and pulling tools, swedge, wireline spear, baler, positioning tool. There are various tools we have in our wireline tools. First of all, gauge cutter. Gauge cutter is a hollow cylinder. This hollow. And you see that there is opening here because when you're moving downward, the fluid comes there and if cannot go out, it will give the tools a wobbly movement. So here we can protect against wobbly movement. This is connected to rope socket or end of the knuckle joint. Correction knuckle at the end of knuckle joint. And these are flat surfaces that for tightening. And also normally there is a fishing neck, this section, a fishing neck that if it gets stuck, then we can call it, we can run overshot and recover that. It is used for determining the depth and diameter available. Okay, I think perhaps a good point to stop and go for lunch break and come back, okay? Thank you very much.
Yes, sir, thank you.
Resume recording. So the first device we want to introduce is gauge cutter. Gauge cutter, the main application is finding the diameter and depth available. For example, you want to run log. Logging equipment, you need to make sure that it can reach to the depth you want to reach and the diameter available. Why they are important? Because this at the end of the tubing, we have what is called no-go. No-go is the minimum diameter in the tubing. And sometimes tubing is blocked because of wax formation, because of a scale formation. Sometimes we have sand production and the depth that we want to log is not available. So when we phone the service company to do this log for us, they ask us, what is the diameter of no-go? And you say that, okay, it's 4 inch, for example. They say, okay, we have a device 3 inch, 3.5 inch. But now you need to make sure that the 4 inch is available, okay? And the depth of that you want to log is available. So you run this gauge cutter. The gauge cutter will be installed here. Yeah, at the end of knuckle joint here. So we have the stem, hydraulic jar. Sometimes we don't have hydraulic jar. Mechanical jar we always have. And then we connect it here. Connect it here. This section is to tighten by a spanner, because round section you cannot grip properly. So this section is for tightening to here, to the rope socket. You see that they have here as well. So they can two spanner and tighten. And then we go and check the diameter and the depth. Because if, for example, this company, Schellenberger, comes and the tools are stuck in the well, you have to pay for their time and for their tools. And you don't want to do that. And diameter and depth, okay? And the top of individual landing nipple of a specific size by monitoring the tension on the table. It can also be used for removing some deposit from the well, the tubing wall. If we see there is an obstruction, then we can use what is called impression block. Impression block is a soft metal and a metal section at this, with the soft metal at the end. We run this one. When we reach to the top of blockage, we slow down until it lands. And then with a jar down, we take an imprint of the blockage. This is soft metal, okay? So we get an imprint of this blockage. And then we can see what is the blockage is. If it is a small deformation of tubing, then we can use switch. Another operating tool that it can open a small blockage in the tubing. So again, you see that you have fishing neck, you have tightening, a spinal thing. So that is one of the actions. Another operating tool is Wireline spear. I told you that we normally weaken the rope at the top of the rope socket. So we are hoping that if tension is too much, it will cut from there. And then we can go with overshot and grab that one and pull it out. But if it cut in the middle of the wire line, then we need to recover the wire. Then we run Wireline spear, that the wire will be locked here, and then we can pull out. If you are lucky, the blockage is removed. If not, at least we are hoping that the wire will cut from top of rope socket. If you don't make the top of rope socket weaker, where is the weakest point or maximum tension in the wire? At the top, isn't it? Why? Because top of the wire has the maximum tension, because in addition to the weight of the tool, you have the weight of rope as well. So, and we don't want that, because then we have a lot of wire in the tubing. Another point, another device is what is called blind box. It's a heavy cylindrical tool, and it is used for jarring down on the top of the fish for obstruction to pass it through the tubing and think about what to do next during workover. But at least if we solve our existing blockage. So if we do our effort to pull it out, the blockage, the obstruction, if you are not successful, then the only option to push it down. Okay? Then bailer. Bailer is a hollow cylinder with a valve at the end. So there is a valve at the end. This is either normally flat valve. So if we have ball or flapper check valve, at the bottom. It is used for removing liquid, solid, debris, and placing chemical. Sometimes the removal of solid is necessary to gain access to the fishing neck of the equipment. All equipment, wireline equipment, they have a fishing net. So, for example, if you want to bring up the subsurface safety valve, and there is an obstruction on top of the subsurface safety valve, first you need to know what it is. Once you found it is what it is, then you need to think about how I can remove it. If it is sand, which was suspended during flow, and now we have stopped the flow and they are settled down and they are on top of the subsurface safety valve. So we can use bailer to recover them. Or there is a blockage, we don't know what it is, we can send bailer to take a sample of it and send it to the lab to find out what it is. If it is, for example, wax or asphaltene, what we can do, we can use bailer to put chemical on top of the blockage. It's called a spotting. A spotting on the top of the blockage. So, dump bailer that you want to inject some chemical, but you don't want to send it from very top, localize, you put the chemical and go to the depths you want and shear down. And release the chemical. Sand bailer, you go jar down and fill the bailer with sand and bring it to surface. You might have to do several times. And sometimes, despite all your effort, you cannot remove all the sand. Then you can use what is called hydrostatic bailer. Hydrostatic bailer, it goes down, but it is sealed. The flapper is sealed. So it has a pressure, atmospheric pressure in the bailer. So imagine this bailer has atmospheric pressure inside that. You go to the depths. Now, what is the pressure at depths? Much higher than atmospheric pressure. So now, if you jar down and open the bailer, it's like a vacuum machine, because it's low pressure against the high pressure outside. So it will suck everything to the bailer. And once the pressure equalizes, then it will close the door, the valve, and then you can pull it out and go with another impression block, see that its fishing neck is clean, and then go with fishing equipment to recover the fish. Any question on baler? Tubing perforating. Tubing perforating, if we cannot open a sliding side door and we needed to kill the well, then you can have above the packer, you can punch, yeah, and make a hole in the tubing. Then you can use this hole for circulating mud. Positioning tool is a tool that can open and close a sliding side door. A sliding side door is I showed the picture yesterday. There is an internal section that can move. And this device is used for moving the internal section. Then running tools. These are the devices that can run subsurface safety valve, plugs, and run to the position. With jar down, they will set, and you can come out, and then if necessary, you go with pulling tools and recover that device. This is pulling tool. So it goes inside the top of the tool you want to pull, and with jar down, it will lock. With jar up, you can recover it. So you see that now, with these devices, we can run and operate a number of tools. This is a pulling tool. You see that it's being locked in the here, and we can pull it out. This is the size packet mandrel. This is screen, sand screen. This is subsurface safety valve. Okay, so I mentioned a lot of this equipment. Any question? So now, if there is no question, we want to talk about through tubing production logging, PLT. PLT is the terminology used in the industry, production logging tool. Now, these tools are used to identify the source of problem. For example, you see that you are producing too much water in the surface. So you need to find out where the water is being produced. if you want, because if you don't know where the water is being produced, you cannot close that section. You can see, for example, annulus pressure is high. So something is leaking. Annulus, do you remember? Annulus, where is annulus? Between tubing and casing. You see that annulus A, B, C that we discussed yesterday. You see that high pressure in annulus A. So that's dangerous. You need to find out definitely what you do. First, you measure the pressure. And then you release the pressure. And look at the buildup. Because if it is building up and it is gas, means that there is a communication. So where is it? It can be one of the joints, the point of contact between joints. It can be the packer, so you don't know. Or a sliding side door is not closed properly, so you don't know. From surface, you see that there is a pressure in the increase, and it's not going to go away. So you need to find out where is the source of pressure. And how you're going to do that is that using through tubing production logging. It's like a patient come to the doctor and say that, you know, I'm feeling sick. What the doctor says, check some basic information, but they send some sample. They need to gather more information. They said that we need to do some tests, and basically through tubing logging is like finding the source of the problem. And obviously, more data you have, the better. So it is used to diagnose mechanical problem. Analysis the individual well performance in relation to the reservoir. Management of reservoir fluid. Which section is producing gas, which section is producing water. Is the casing, tubing, or packer leaking? Is there any internal or external corrosion problem? Do we have the flow behind the casing? Behind the casing. Is flow inside the casing moving to teeth zone? Teeth zone are section of the reservoir high permeability, and they are taking the fluid instead of producing it to surface. Or some zones are not contributing, or some zone only contributing gas or water, or contributing zone producing up to the potential shown by other data sources. Where are the injected fluids going? Is it going to right formation? How much into each zone? These are information that you need, and you cannot get it by monitoring the well from the surface. Which zone needs to be stimulated? When we do a simulation, where the fluid go? This simulation achieve the desired result. For reservoir management, what are the initial fluid saturation in each zone? What fluid saturation changes occurred during the production of fluid movement? Is the reservoir being depleted in the desired manner? So you see that a lot of information we can get from production logging tool. The devices we have in production logging tool are a lot of devices. First of all is the casing color locator. You remember I said that the connection between two casing or tubing has higher diameter, has higher, more metal. Remember that. Temperature devices, we can put devices that measure temperature. Pressure devices, we can measure the pressure. Densitometer, yeah, measuring pressure at 2 points, and then you find the density. A spinner flow meter, these are devices that if there is any flow, they will rotate like a fan, and we can monitor the speed of their movement, and then we can do calculation how much is flow. Noise detector. It's like listening devices. They go down hole and you detect the noise. Cement evaluation tool. Because I told you that cement is very important. If you don't have good cement, then you are going to have a lot of problem in future. There are other devices, radioactive tracer and detector, pulse neutron devices, gamma ray neutron devices. So there are a lot of devices that we can put in the production logging tool. So the set is, as I said, like a doctor, there is a problem, we need to, or the problem of production logger is to put enough clues together from every source available to develop an answer with an acceptable confidence. So casing color locator is a location of connection between casing. See that? That's one, that's another one, that's another one, that's another. Basically, it is a coil between two magnets, and the electricity provided is depend, because you are moving, that will change the magnetic field, and depending on the mass of the pipe or that section of the pipe, it gives you a signal. So the color, the point of joining two casing or tubing, has maximum mass. So it will show color location. So this is the color location as we are moving up and down. So this is A is running down, B running out, up. That is the difference is when you are moving down, there is not much tension on the wire. When you are moving up, there is a tension. And that will result in wire to expand. So 6 feet, that's 2 meters. So normally, we run gamma ray in the beginning. Gamma ray is the signal from gamma ray depend on the nature of the deposit in the well. And the gamma ray is reference log. It is reference log. So the first gamma ray, they run everything else, whether the depth is correct or not, is correlated to this initial gamma ray. And if you run a CCL and gamma ray together, then you can relate CCL against gamma ray. Then you don't need gamma ray. For gamma ray, you need to apply electricity, and you want to avoid electricity when you are perforating. Because it might result in misfire. So then we put CCL. Now our reference becomes CCL. For that reason, we need CCL. Temperature device. Temperature device is a Bitson bridge. It's basically a temperature sensitive resistor. The resistance of that bridge depends on temperature. I don't know if you are familiar with Bitson bridge. It is something like this.
Second year of my bachelor's, it was 2008. I can't remember anything from these things.
Yeah, really. Yeah. And this is basically you have similar resistance like this, and there is power supply, and you measure the current here. So there is power supply, there is measured. One of these resistors is thermistor. Means that the resistance changes with temperature. So when the resistance changes with temperature, then you can measure temperature. With calibration, you can measure the temperature. Obviously, you need to do calibration. Now, thermistor can be used to identify different zones. Because different zones, this is shale and shale salt sequence. This is shale, this is salt. And this is temperature, this is depth. And you can see that there is one slope here, one slope here. Because salt and shale, they have different thermal conductivity. Because they have different thermal conductivity, the temperature change will be different. The slope of temperature change will be different. Or here, shale and sand sequence. Yeah, again, you see that the slope is different. This is the sand, I believe, and then this is the shale, was close to this slope. So we can use temperature to identify change in the formation. A spinner flow meter. That is used to measure the flow overall or flow from different zones. The most popular one is this one. This one is the most popular. So if the fluid is moving and then this spinner, will rotate. So we know that there is a flow there. Density, it is measuring pressure at 2 points. And from that, you can measure the density as 2 points at 2 feet apart, and you can measure the density. Because the pressure difference is density multiplied by the length, and that's related to density. Noise. Noise depending if it is single phase or two phase, the noise amplitude would be different. And we can measure the noise. This is particularly useful if the flow is behind the casing, because it makes the noise. You don't see any flow inside the casing, but outside the casing, you can detect the noise. Caliper. Caliper, again, by measuring electrical resistance, because that connection is here, and depending how small it is or how big it is, the caliper position will change. Measure the internal diameter. And now we have 64 we can have 64 arm to take a good map of inside the well. Multi-arm caliper, measure metal loss due to corrosion or erosion. And they can be used in open hole completion as well. If there is formation has partially collapsed, you can use that. So combination tool is something like this. So this is casing color rotator. This is thermometer. This is densitometer. This is caliper that shows the size inside the tubing. This is pressure measurement. This is density measurement. This is flow measurement. So this is a rope socket in a way. Yeah. So one case like this. We see high pressure. This is the tubing. This is the tubing. Tubing here. This is the annulus. This is the annulus. We see high pressure in the annulus. And what you do, you release the pressure. You see that the pressure again building up. You take sample. You see that that's reservoir fluid. So something is, somewhere is leaking. You can run temperature log and while the well is closed. While the well is closed, temperature log will show geothermal temperature gradient. Temperature log will show you geothermal temperature gradient. Geothermal temperature gradient is around 30 Celsius per kilometer. Okay? And you see that here deviate and is cooler. So what does it mean if it is cooler and deviate? You see that here we have Joule-Thomson effect and temperature has dropped. So there is a leakage. Where is the leakage? Is it at the bottom or at the top? This section. Yeah. It is at the bottom because it's cooler. Joule-Thomson effect. So this tubing, there is a hole. And now what we do? We need to decide our next step. We can run caliper to see that how severe is the hole. Or there are some devices that when they experience a change in pressure, they will solidify. Or you can put a patch on top of this. Or maximum is that you need to pull out the tubing and repair it. So there are various options, but you need to first find what is the problem. Another one is combination 2. Here, this is a flowing well, and we want to see which zone is producing water. On the surface, we see water, but we don't know where the water is coming from. You can run the flow meter and you see that there is no flow at the bottom here. Okay, so this zone is not contributing. Okay, and then you come here, there is some flow here. So this zone, these two zones are contributing. And then you see more contribution up to here. This zone is not contributing. This zone making a lot of contribution. Okay, this upper zone is not contributing. This one. This one. Okay, but what they are contributing? Here we measure density. 2 units for density, 0 to 2, and the dash line is 0.7 to 1.5, 1.1. This is 1.1. This is 0.7. You see that the density at the very bottom is 1.1. So this is water. As we are moving up, the density drops. So some oil is being produced. And there is no production here. And then more production here. And it's mainly light component because density has dropped, but it could be the same oil because it will dilute the water what we were producing. Because here we have a lot of water, a slight amount of oil. Here we have a lot oil and a small amount of water. And therefore the overall density has been reduced. Okay? From here, we see that the bottom zone, the two bottom zones are producing only water. The zone C is producing some oil. This is C. You see that the amount of water has been increased, but there is some oil as well. So if you want to avoid water altogether, you need to block this section. Here. Then you have removed all the water. But if you don't want to lose the production, here is small amount, 50-50, maybe 60-40 is water and oil, you can put the blockage here. So here you put the plug. That will remove majority of the water and also produce some of the oil remaining. Any question?
No.
Now, this is another one. This is a shutting rock that the well is closed. The well is closed and you run the flow meter and you see that although the well is closed, but there is some flow. The spinner here shows that the oil going upward. Here, it shows that the oil going downward. You see that? This oil is going downward. So it shows that the oil, that there is no production on the surface. It's zero. There is no production on the surface. But it looks like the oil is being produced from this zone and being injected this zone and is being produced from this zone and being injected here. That is not very good news. So how we get this information? First of all, we look at where we don't have any flow. At very top, we don't have any flow. At very top here, we don't have any flow. And here we don't, at the bottom, we don't have any flow. So temperature here is geothermal temperature. And here, at the very top here. Yeah. And we can connect them together. That is geothermal temperature. If there was no flow, we had to follow this temperature. But you see, the temperature here is higher than this temperature. What does it mean? It means that the flow is from bottom to top. Do you agree? Because bottom is warmer. So we understand fluid here, although the well is closed, is moving upwards. That's why it's warmer. And here, if you look at the temperature, you see that here is lower than the geothermal temperature. So here, the formation is producing oil, which is going downward. Here, the oil is going upward. So the oil is being produced from this perforation and goes upward and injected here. The oil is producing from probably this formation and then increase with this formation and then decrease here, and they are being injected here again. It shows that the different perforation or the different zone with different permeability. And because there are different permeability, some zone will contribute more to production. And when the well is closed, that high production zone pressure is lower, and the flow moves from high pressure to low pressure. And also, another interesting point, another interesting point is log up and log down to measure the amount of flow. Now, if you have a fan, you know, like Moses had top of his roof, ceiling has a fan. Now that fan will push air downward. If switch off the fan and we move air upward or downward, the fan will rotate. So flow meter is for measuring the flow if it is stationary. But if it is moving, it shows the upward on downward flow. First of all, we need to calibrate flow meter. So we take the flow meter to section that we don't have any flow. So here, you stay here, you see that it doesn't move. Now, you move it with a certain velocity, for example, 1 meter per second. Now the fluid is constant, the fan is moving. You know the fan movement, you know the diameter of casing or tubing, so you can calculate the flow rate. Yeah. So this is for calibration. Here, this is log down and this is log up. Log down, when we move the PLT tools downward. Okay? If you are moving downward, section is not producing, shows this flow rate. But then it comes down and then comes down more and then goes up and then go back here. You see that that is the same point so here you see that is reduced and then reduced further and then building up and now being up and going back to the same point. So this is a good log because where we don't have flow, they show the same value. Here is reduce. Reduce means that the flow in the direction of movement. So flow is going downward, the tool is going downward, so the RPM, the rotation is reduced. Here goes down, you know, so it means that a lot of flow is coming in this direction. And then you see that it's building up, so means that the downwards flow is reduced. Here we have upward flow. You see that it's higher than the here. So the flow is upward, but not a lot, okay? So maximum downward flow here, maximum upward flow is here. So that we match with our interpretation here. This is called lock up, when we go to the bottom of the well and pull it up, okay? You see that here, the flow, first of all, log up, you see that here, the base, and it is reduced, means that the flow is upward. And then here, the flow is downward. The flow is downward. And then go back to the line. So both of these will help us to identify the direction of flow. What is flowing? Look at density. 1.2 up to here is water production. And then we have some oil production. Yeah. And then we have, here we have mainly gas, because density is 0.2, 0.3, something like that. So you see that with this technique, we can find out which fluid is being produced, which zone, and whether we have cross flow or not. Okay? For running cement evaluation tool. Cement evaluation is that, as we mentioned before, cement is very important. And if we don't have a good cement, we are going to have a lot of problem with the well. And that could be corrosion, because cement will protect the casing from corrosion. So if we lose the cement here behind the casing, then we can expect corrosion, because salty water can go behind the casing and cause corrosion. And also, cement has a role, important role, on the integrity of the well, because you don't have cement, the weight of the casing itself will cause a lot of problem, buckling, deformation, shear. So cement is very important. So we need to find out if you have good cement or not. You might say that, okay, if you have bad cement, what we're going to do? If you have bad cement, we need to cut the casing and then inject cement, or perforate the casing and inject cement. Anyhow, we need to have good cement. So this is one of the devices that can measure the quality of cement evaluation tool. It is used to identify mud channel, whether we have mud channel behind the casing. It is 8 ultrasonic transducer arranged helically, so around here, every 2 feet. And they can transmit the signal, and the signal return and the amplitude and time is very useful in evaluating cement. So that is the cement evaluation tool. If we have bad cement, the amplitude would be high. If you have good cement, the amplitude would be low, because the sonic wave has to vibrate a larger mass. Imagine that if you have an empty glass and you hit it with a spoon, compare the filled glass. The glass is full of water, and compare the two. The one which is empty has higher amplitude. The one which is full would have very low amplitude, because the low, high amount of water, the vibration should also affect the, is dampened by presence of water. Okay, so some tutorial. In a gas well, high pressure has been recorded in the annulus, suggests a step to taken to diagnose the problem. Maybe we leave it for tomorrow. Maybe it will, when we repeat it, it would be helpful. So there is another one, another one, another one. And this is some of the logs. This is a multi-caliper logs that can measure the amount of corrosion, and also this is gamma ray, yeah, shows the different type of fluid we have. So you can run these sorts of logs This is logging history. That's cement bond log. You see that transducer and receiver. Transducer create the vibration, sound waves, and sound waves has 3 paths to go. One is the fluid. It can go through metal, and it can go through formation. The fastest one would be metal. The next one, cement. The next one, formation, because they are solid. The speed of sound in solids is much higher than fluid. So the last one is the, so shortest path is this one, through the metal. If cement is not attached, then amplitude will be high. So here you see that the casing arrival, that is metal arrival, formation arrival, and then mud arrival. You see that the velocity in the mud is much lower than casing. And this is a variable density log, VDL, that demonstrates the quality of cement. And here you can see better. Here you can see that the amplitude is much lower. That means a good cement. And this is a bad cement because amplitude of vibration is very high. This is CCL. This is CCL. And this is gamma ray. So that is one application of logging. That probably is not necessary because we're talking about drilling. If you are interested, I can expand on that. Measurement while we are drilling. But some of the devices that we use for wireline services, as I said, sometimes we use cranes. And this is a stuffing box here. And this is the pulley, one pulley at the top here and another one here. Another picture. And you can see much better now. And this is the rope, wireline. This is a wireline. Goes to the stuffing box. And from here, the wireline comes here. And I don't know if you can see it. This is the wireline here. What is this one? This is a line that we apply hydraulic fluid to seal the gland here. Because wire pass through it, and we need to adjust the pressure to prevent leakage, but at the same time, not too much friction. So another one. Here is some of the tools. Which is normally back of the truck. This is the wires, wire drum. This is the odometer that measures the depth. This is what you see from the truck. And this is odometer, the measure the depth. And also not very good winding here. Normally you have to be very careful and line by line. And that's it. Do you want me to talk about, oh, this is me. Can you find me?
You're the one with the glasses.
Which one? This one?
I think.
This look like Woody Allen. That's me. That's me.
Oh.
Yeah?
Have you been working for Schlumberger?
No. I was working for NIC, National Iranian Oil Company, and Schlumberger was providing service to us. I was field engineer. And can you recognize me here? Yeah. You don't see this good-looking guy? That's me. This is with National Iranian Drilling Company. So we were using Schlumberger and National Iranian Drilling Company for logging. Okay. Do you want me to explain the LWD and MWD, or you are okay?
It's up to you if you think
okay.
One of you? Sorry. Yeah, that's enough, because this is more related to drilling. But if you want, I can explain very briefly. Measurement while drilling, basically you measure the direction of the drilling and the pressure on the bed. Yeah, weight on the bed. And logging while drilling, this is measurement while drilling. Logging while drilling is that you also have gamma ray that determine what type of formation you have. So you are logging means that finding what type of formation we have and fluid we have and things like that. Measuring while drilling means that you want to find the direction of the drilling. Normally we have to stop drilling and run a direction device and then measure the direction. So this is fine. The beauty here is that how to transfer signal to surface. Yeah, because we don't have a wire, how we transfer the signal to surface. Here, the clever idea is that to create pulses, pressure pulses, and the pressure pulses will pass through the fluid. And there is a surface system that, so it's downhole system with that all the measurements are converted to pressure pulses. And then on the surface, these pressure pulses is converted to reading. Yeah, it's like Morse. Morse, in the old ages, we didn't have telephone, we don't have, we have telegram. That was Morse signal. For A, you had a line, and for example, a point, line was longer than point, and with this different combination, they had all the letter. And this was passing through lines and then be translated in the receiving end. This is something similar. So now with pressure pulses through the mud column, we can measure the direction, we can measure the type of fluid we have, we can measure the porosity, we can measure whether it's a shale, whether it is sandstone. So we can do this sort of measurement. The limitation is that how many channels you have for transporting information and how often you can transport information. But this is something that is available at the moment.